Okay, so let's introduce the P-series test real quick, uh, and maybe kind of introduce comparison tests. What I actually want to do today, I don't want to spend the whole time lecturing. I do want to actually break off into groups and work on. There's two activities on comparisons. So there's an introduction to comparison tests, and then there's another comparison test activity. And then the project for this week will be, I think it's Thursday, is an actual project on comparison tests. So it seems like people were still kind of struggling with this with indefinite integrals. So we'll get a lot more practice. Essentially, all the same rules are going to apply. So our p-test we essentially just want to ask when does the series converge or diverge? Well, by the integral test, these two things will converge or diverge simultaneously. And well, this one we actually already know. So what values of p do we get convergence or divergence? So let's write it out. So the same rule. Same rule applies. Which means this guy will converge when p is greater than 1, and it will diverge. Yeah, p is greater than 1 for p less than or equal to 1. The nice thing about series is we don't have any sort of like asymptotic behavior to worry about like we did with these improper integrals. We need to worry about functions and potential asymptotes and how a function behaves near that asymptote, whether it approaches the asymptote closely enough. Since our series are always 1 to infinity, the integrals are always these infinite type indefinite integrals. And so we really only have to worry about this one case where we're sort of integrating or summing out to infinity. And so we really just need p bigger than 1. So 1 over n squared, we can add all those up. It'll converge. 1 over n to the 3 halves, still good enough. We can add all those up. It will converge. So nothing too new there. And the usefulness of this is, well, now I can say convergence or divergence really of series that might look a little different based on comparisons. So let's go over some of the basics of comparisons before we break into the activities. So we want to know something like, does the sum of 1 over, let's say, n squared plus n converge or diverge? Sorry, was there a question? Or just a little mic blip? So converge or diverge? Well, in this case, we can compare at least what are we adding up? 1 over n squared plus n. The denominator, what's the highest power? Denominator is just a polynomial. So with polynomials, especially in the denominator, we want to just kind of compare the highest power. And we have n squared. So we want to compare this with n squared. And if I'm adding n, when all of my n values are positive numbers, if I'm always adding a positive number, that means my denominator is going to be bigger than just 1 over n squared. And so because of this, we can arrive at similar rules. So I know that that series has to be less than or equal to the sum of 1 over n squared. One thing I do want to emphasize is they're also both bigger than 0. So they're both positive because we're always adding positive numbers together. We will deal with alternating series here soon where we are adding both positive and negative numbers together. And we have to be careful with that because if a series is negative, it could theoretically go to negative infinity, which would diverge. But because both of these are bigger than 0, and now I know this guy here on the right will converge. So let's say strictly less than infinity. Or if you want, you could say equals some constant. I know I can add all these numbers up and get a constant, get a number strictly less than infinity. It will converge. Therefore, the smaller sequence also has to converge. I can add up all of these numbers and get a finite number. And this is the basics of our comparison test. Essentially the same thing we were doing for indefinite integrals. Essentially now we're just comparing our discrete functions, our sequences. Okay, we also need to get into the limit comparison test. So that's going to come up today. What about let's do something a little different. Let's say something like 1 over n squared minus, and let's just say a constant, minus 7. Let's say n equals 3 to infinity. So the only reason I'm starting at 3 is because I don't want to deal with negative numbers. But of course, the place where we start doesn't quite matter in terms of convergence or divergence, right? It's really the rate of growth or the rate of decay of our series as we're getting out to infinity. And the problem with this guy is that, well, since we're subtracting, the denominator is smaller than if I just got rid of, if I'm just comparing the highest power, which is what we want to do. We want to think of this thing as something like 1 over n squared, but because we're subtracting the 7, the denominator is smaller. So we would only get the fact that our 1 over n squared minus 7, it's actually going to be bigger than 1 over n squared, but only by a little bit. And this is, of course, for n bigger or equal to 3. And of course, because of this, I can't really say anything. All we have is that the sum of this series is going to be bigger than the sum of our other series, our 1 over n squared. And I know this is a constant, but what does it mean to be bigger than constant? Could be a bigger constant, or it could be infinity. So we can't get a conclusion there on convergence or divergence. What we're going to see instead is our limit comparison test. And this will come up, I think you will kind of rederive it, or at least re-intuit it on the activities. But what we want to do is compare the ratio of the rate of growth of two sequences. So this is going to be very similar to like L'Hopital's rule. Really what L'Hopital's rule sort of incorporates is we were comparing the ratio, right? The ratio of two functions. We always have a numerator and denominator, and we're comparing either the rate of growth or the rate of decay of those two sequences. And L'Hopital's rule is kind of just a special tool that allows us to say, hey, if we get something like an infinity over infinity, then we can sort of pass that ratio to their derivatives. And we can keep doing that. We can keep passing to consecutive derivatives as long as we're getting these infinities over infinities. So, well, let's compare our ratio. We want to compare the ratio of 1 over n squared minus 7 to 1 over n squared. And I want to know how these two sequences behave, comparatively speaking, as our limit goes to infinity. And so all of these tools for computing these limits still come into play. Got to remember all your algebra. So dividing by a fraction, I always like to just multiply by the reciprocal. Always a good first place to start. And then you can either do L'Hopital's rule here if you wanted, or this is a polynomial. So what is a polynomial? When the powers, the highest powers of the polynomial are the same, it will converge at infinity to the ratio of the coefficients. So what is this telling us? This is telling us that these sequences at infinity are essentially behaving in a one-to-one manner. That this -7, it doesn't matter, right? We've talked about this a lot in like pre-calc, if you think way back, when we're computing these limits to infinity or finding horizontal asymptotes. If I'm, if n is getting really, really large and n is getting, to 1,000,000 and I'm squaring that, subtracting off 7 isn't changing that number by a big quantity, relatively speaking. And so really the difference between n squared and n, there almost is none as n gets bigger and bigger. And that's really, what we've just kind of shown here. So what does this mean? It essentially is going to say that since the rate of growth of these two functions is the same, meaning also the rate of decay of the reciprocal, so 1 over n squared minus 7 and 1 over n squared both decay at the same rate, which implies that these two functions, we start at 3. they will converge and diverge simultaneously. Because we got a constant here that is non-zero. So we'll see that a little bit more in the activity today. What happens if the ratio is infinity? Or what happens if the ratio is zero? Zero and infinity are, you should kind of think of these as almost like the opposite numbers of each other in terms of their multiplication properties. They're both very similar, but they're also kind of like the reciprocals of each other. As we've kind of seen with a lot of these limits, we know that 1 over infinity is 0. Well, if I take 1 over 0, we kind of think of that as like infinity. Could be positive, could be negative infinity. And so if I get a 0 or infinity here, because we're comparing 1 over that, or just infinity or 1 over infinity, we want to be careful of these cases of zeros and infinity here, because then it's telling us that one function is essentially dominating the other. It's going to go to infinity much, much faster. So we have to be careful with how we can conclude based on that result. However, if we get a constant that's non-zero, we will essentially always get convergence and divergence simultaneously out of the two sequences. So our last conclusion here would be, since they converge or diverge simultaneously, and then by our p-test, one over n squared converges. So 1 over n squared minus 7 also converges. Any questions on that? Okay. So, excuse me. Sorry. Let me share real quick. So what I want you guys to do, the activities for today, if you go to just the activity section, so go to projects. Are you guys seeing that full screen? Let's see. Go to activities and then look for the comparison tests. So comparison test discovery and comparison test practice. The comparison test discovery is just outlining the basics and kind of comparing, well, which ones will converge or diverge based on some simple comparisons. And then kind of we'll walk you through the comparison tests, as well as kind of get a feel for this limit comparison test down here at the end. And if you guys are good at that and you guys are moving through, do the practice one. So the next one's just comparison test practice. It'll reiterate the comparison test and the limit comparison test there at the top, and then just give you a lot more practice problems to get a feel for those. So let me go ahead and create the breakout rooms.